indication of a globalized instrument manufacturing tradition. Then we got what we can call a vent hole below the sleeves. So you got the rotary sleeves, holes you can open and close, but here on this pipe you got one hole at the end which obviously had no such sleeves. So this was the lowest note. You couldn't cover it either with the sleeves and very probably also not with a finger. So the bass note would come out of this hole and the end of the instrument itself would not produce a musically usable note. So it might be there to alter the sound of the instrument a little bit, but not the pitches the instrument produces. The same we find on what we call the short pipes at Meroe, which are not that short. They are partially longer than the silver pipes from Pompeii, but they are shorter than the long pipes from Meroe. Yeah, so this here, the lowest hole here is also without the sleeve. We got a bell even lower, but the bell would normally not be accessible unless perhaps you're in very low fingering position and cover the last hole. But this has not got a sleeve. Then we got wooden core sections, which are probably responsible for the disintegration of so much of the evidence because the wood shrinks, then there's nothing to sustain the metal, and the metal is very, very thin. It's just 0.5 millimeter, 2/3 of a millimeter, and so the corroded metal would just collapse. And again, we find this in Meroe, so the short pipes also had bone cores wherever there was a mechanism, so where you absolutely need to maintain the cylindrical nature of the sections, because if you get wood and the wood expands with the moisture and distorts the cylinder, then you would get your mechanism jammed. But wherever there was no such mechanism, both at the upper and at the lower bites, they instead supplied sections with olive wood cores, which makes sense both, as Kamila said, both in terms of economy and of weight. I will now focus on one very probable pair here, which is A and B, for a variety of reasons. First, we have a high degree of certainty that these might belong together, so their diameter is unique within these cage of pipe fragments, so none of these could have been the second component of another pair here. The fragments stand apart for various reasons, and no other pairing is possible. Almost all parts survive, as we have seen. Only here we get apparently a missing part, but actually we might have this preserved as well, because you can see this fragment here, which was jumbled together from one bronze shell and one bone core in a way that is apparently wrong, because whoever pushed the bone core in here and pushed it so hard that we can't get it apart at present, paid no attention to blocking a finger hole without giving it a matching hole in the bone core. So this must be wrong. And that's not the whole story, because inside it, there's another bone core, which was of a much smaller diameter, so that it fitted into the first bone core of a large diameter. And if you look inside it with an endoscope, you can see here that there is the border between. You got a nice step. So somebody thought it would be a good idea to get most of the fragments, so kind of, catapyknosis done. Well, I don't know. And in addition, I thought, okay, I can go there, and we don't know whether we have an index hole here or not. But I got the endoscope, and in order to prevent even an endoscopic survey, they stuck some folded metal sheet inside the small thing, so we can't find out, because it's inside the bronze, it's inside the bone and it's shifted. So we need to take this apart in some way to find out whether we had an index hole there. So I doubt with getting the thumb hole that anybody could reach that steering hole with the index finger. So I rather think there was an index hole, but this needs to be established. At least I could get the length of the thing, and the length is exactly, meaning to the millimeter or the half millimeter of what is missing from the photograph. So I established both measurements independently and afterward looked it up and they were good. Yeah, about the methodology. The best way of working with that photograph is on screen because you got the photographic distortions, so different zooms, zoom factors are necessary at different parts of the photo. So you lay your screen flat, you position some existing fragments around what you need to measure, then adjust the zoom that you get these nicely covered, and then you can measure beneath, adjacent to them what you don't have preserved, and you get hopefully a quite decent measurements of that. So that's what we've done here. So what we still do not have is the bell of B, which probably just crumbled into non-existent, being mounted on a wooden core, and we had to measure these on the photograph as well. So what we probably will never know is, was there a vent hole on the bell of B, just as there was a vent hole on the part of A? Because A got the bone throughout, so this hole is present, because there was just such a small part below the last hole with the sleeve, it didn't pay off to add such a short section of wood. In B, it was a longer section. We might never know. So we can put this together. We got almost all the finger holes, perhaps missing one, probably missing one index hole. So we can feed this into our software and search for a harmonicity optimum, experimenting with different lengths of reed, because that's always the factor we don't have in the evidence. And that's the result if we plot it as a graph in shades of gray, and you may spot we got an optimum around here. We can transfer this to a three-dimensional graph where you can see how good it is. At any rate, it's right at the diagonal, which means that it's there where we expect it, so that both reeds are at almost identical lengths, and it doesn't look funny because one reed is longer. Who would make such a pipe? And this is a three-dimensional representation, and you can see that's the optimum here. It's far above the random noise of smaller side optima, which we get anywhere else. So that's a very good chance we have the harmonic configuration of the pipe. And that then transposes to frequencies, and so to pitches, and so potentially to notes. So you got the parameters for this graph here covered. And now what does this mean in terms of ancient music? Can we find a meaningful interpretation for that? We need to look also at the practicabilities of playing, because we have not only rotary sleeves for single holes, but in two cases we have modulating sleeves, meaning, so this is just a schematic representation, meaning that in two cases, two adjacent finger holes are covered by one sleeve, as far as we see, in a way that you could only open one of these two at once. So that means two notes, only one of which was usable at one time, and this should tell us something about the modes in which this was usable. Yeah, modes. This is the 15-key system, or the respective part of the 15-key system of late antiquity projected onto the pitches here. So the high frequencies, the high notes are to the bottom. Sorry for that. It's because of the practicabilities of all of calculation, and the rest of the base nodes, these are short pipes, is just vanishing out of our screen here. Yeah, let's have a look. These are the two alternate hole pairs. So we only can have one of these two pairs of the orange stripes. That is the whole arrangement of the lower pipe when it was surprised by the eruption of a volcano. So that's how it was interred, the setup. Where does this fit? Among all these scales, it surprisingly fits on the Hyperdorian scale, right at the flat end of the entire system. And also part of the Dorian. The Hyperdorian is the Dorian extended, modulating to even higher region. So, in this case, we have the lower double sleeve upwards, the upper node, and the lower node in the second. So, what you can see here, up and down. One of the four possible configurations of two binary OR gates. Yeah, if we move this upwards, we get to the next level, which is hyperphrygian. And we can easily supply missing nodes of the hyperphrygian from the other pipe. So up, hyperphrygian and part of Phrygian, and then we switch the other one to low, and we can down up, and get, down up, what do we get here? Interestingly, we get also Phrygian, but the chromatic variant, not the diatonic, but we now get two semitones chromatic Phrygian. That's something that is established in the musical fragments. The Asenius Pian has chromatic Phrygian. No, yeah, at this region, not typically, but we get it. It's a very high-pitched pipe. If we switch those two holes, finger holes, potential finger holes, to the lower variants. So these are not OR gates, but you only got a couple of fingers. So you need to be a bit careful with not running out of fingers if you got only 5. Then we get to a configuration that fits here to hyper-Iastian. And we need to leave out all of those Lydian keys here, because those would require both of the OR gate separated fingers. So we can't get these. Again, we can supply missing nodes from the other pipe in the playing position. So that the higher pipe, interestingly, has a gap of about a fourth. So you play on the higher notes, and then you still can reach the lower note with the pinky, because it's such a high-pitched pipe, have I mentioned that? And so the holes are still close together. And then you get any of the bass notes as well. And so you can put together a very nice hyper-Iastian octave. So down, down, hyper-Iastian. That's a funny assortment of scales if you look at this, because hyper-Iastian normally would be a Roman period scale, the others would be Hellenistic scales, not attested later. What does it mean? We can get, if we look at what we have, also some Dorian, complemented from both. We can get some Phrygian from both pipes together. So, a lot can be made, but not Lydian. We can't get a nice Lydian, but we can get a lot of Phrygian and a lot of Dorian, Hyperdorian, Hyperphrygian around. In addition, we have a teardrop-shaped finger hole for the middle finger of the higher pipe, meaning this was clearly meant to do some half opening and getting even a higher pitch by opening the whole teardrop thing. So this got a range built into the one hole, which gives us access to, if we calculated it, the lower pitch, this, and the higher pitch, probably these pitches here. So this complements the scales in its two positions for a single finger hole and makes the whole thing even more accessible. Yeah, that's the 15 scale system nomenclature. But we have an older nomenclature, which is not that well known because it's not present in the tables we usually consult first in Pöhlmann's edition, Pöhlmann West edition. Those normally use the full, or in Alypius. Alypius is late in this 15 scale. So our brain is hardwired to the 5 scales with the hyper and hyper variants. But Aristoxenus, and also reporting systems before Aristoxenus, used the same terms for Dorian and Phrygian, and not for others. They had low Mixolydian in the stead of Hyperdorian. They had high Mixolydian in the stead of Hyper-Eastian, corresponding to the Mixolydians of 2 rivaling systems before Aristoxenus. And instead of Hyperphrygian, Aristoxenus coined the term Hypermixolydian. So if you view it through the lens of the Aristoxenean nomenclature, you get a lot of Mixolydian in different flavors. And this Phrygian and Dorian and Mixolydian looks a bit more consistent than Hyper-Eastian, which doesn't have a good meaning. So final observation here with this Hyper-Eastian or high Mixolydian, we seem to have 2 different notes for the same diatonic pitch, whether you take it from this funny pitch here in the lower pipe or this pitch here on the higher pipe, which corresponds well with either the diatonic of the normal tuning or a soft diatonic tuning in the lower pipe. So you could probably play different flavors as well. But let's have a look at hyper Mixolydian as scales in our ancient treatises. And I try to show you that our normal filter through Alypius is not what the ancients thought, not the system the ancients used to think within until very late times. So he starts with Cleonidas, so it's not very well dated, but when he's talking about modulation, you can see here, he's talking about hypermixolydian, which is not the later system, which is the earlier system. So this may be not so long before Pompeii got destroyed. Phrynicus, about the right time here, talks about modulation, Dorian into Hyperdorian, or Phrygian into Hypermixolydian, again, Hypermixolydian as a thing, not some construction, but as a musical thing that you would quote just if you refer to some modulation, so something that you might have heard in discussion of musical matters. And he distinguishes modulation from retuning. So modulation within one melody, retuning, you stop, retune the instrument, being the aulos, closing and opening, or the lyre, retuning the strings. So in this case of the aulos, somebody has piped in the Phrygian key, finished the melody, and again changed into another key of the 13 harmonia, and that's the 13 of Aristoxenus. That's not the 15 of Alypius. So again, they didn't think in the 15 keys in that period. Even Ptolemy, already a couple of generations after the destruction of Pompeii, was talking about Hyperdorian and the key 1 octave higher, the modulating octave key, which again he quotes most naturally as Hypermixolydian. No talk about some sort of Hyperphrygian. Anonymi Bellarmani, often attributed to quite a late age, but without really a reason, when talking about the regions of the voice, talk about Mixolydian, Hypermixolydian. Again, the same paradigm in which we are. So, apart from Aristides, who has the 15 keys, and Alypius, and they are 300s, and later we have nothing. So, it seems Yeah, Aristides quotes both systems, and he says, yeah, 2 Mixolydian, lower and higher, and he got noon, now, and he's very aware of now, and we don't know when this now started, but when he goes on to Hyperlydios, the additional 15 system keys to the 13, Hypodon Neoteron. Again, something that sounds like not very, established in his time, but still acutely aware of this being quite new. So, to sum up, in the times of Pompeian before, we definitely should think in Aristoxenian terms and should regard Hypermixolydian as a musical entity, not a theoretical construction. Yeah, what is it? Yeah, from Plato on we know that Mixolydian, or what sounds like Mixolydian, should be dirge-like, which implies probably a high pitch. Did I say these are high-pitched instruments? So we might have an explanation here, a very much Mixolydian instrument, a very high-pitched instrument. And it goes even further. On the left, on the higher pipe, the right-hand pipe, if we have established the fragments correctly, and others have done this before us, there's no index hole, but the index can reach up to the Syrinx hole. And this is the only instance of an index operating Syrinx hole we have. What are Syrinx holes normally? So opening it at least triples the frequency. It's not going to the octave, it's going to the 12th. So we got Syrinx holes on Megara, Hellenistic pipes, on Pompeii, one of the silver pipes, on Meroe, the short pipes, and they all are not operated with the index, but they need to be operated independently. They are opened, you need to stop playing, operate the Syrinx, start playing again. So 2 different playing modes, like Aristoxenos was quoting. So if a pipe is one pipe playing in Aulos mode, the other pipe playing in Syrinx mode, 2 different ideas. We got a Syrinx on the wooden pipe in the Berlin Egyptian Museum. This also serves to extending the scale to the next degree, but again you have to set up the Syrinx hole and its opening beforehand. Open, closed, half closed, all may have a sense, but you can't operate it while playing. But here with the Syrinx, with the index hole, you seem to have frequent jumps between the 2 registers, which are so far apart because you can just tap it with your index finger. So this is something different. Some playing mode we have no idea it was around anywhere before. So there's a significant gap in the scale between the 2 modes. And interestingly, we have the Mixolydian Harmonia. And when I first built the pipe playing this back in 1998, I think I also resorted to getting the highest pitch by overblowing, because you can't finger that. The gap here is a tritone that's much too large for any fingering, so you need to have a bass hole and then just overblow to the highest note. It's a natural thing to do on an Aulos to get a scale like this. And this idea of Mixolydian and overblowing might have made it, just as a general idea, into the design of those pipes we have here. Yeah, does it have to do with the term Kenitsen we once find in comedy as a description of what Aulos playing does? Goose-izing, sounding like a goose. Timotheus, otherwise connected with the idea of high-pitched shrill sounds, of terrible sounds. Yeah, the goose. What does a goose do? It's not only some kind of quacking, but typical for the grey-leg goose, which is the ancestor of our domestic geese, has a low rumble, and sometimes it intersperses a high-pitched sound and then goes back to its normal frequency. So that might be the idea, and that's what you really could do with the index finger releasing on the camera. So yeah, as a conclusion, probably we have high-pitched pipes with the idea of mixolydium and probably thrinotic associations and the possibility to access some Dorian and Phrygian in between quite as well. Thank you. Yeah, or I might play this. So that's the reconstructed pitches, and we could just, yeah, let's see. Might really be made and tuned for playing in that higher register because that fits together surprisingly well. Yeah, we have no time to make a reconstruction, so it may be still some time until we can say remade are the pipes that were broken, new sound from this fragment shell spring.
You can ask for questions. Yes.
Thank you. That was really, really interesting. And we've spoken about syrinx holes on the Reading Aulos and some ones that are going to be published from Gordion, which will be quite interesting to fit into this development of whether it's a playable kind of thing or something you set up. But with some of the photos, did I see that the syrinx hole was sometimes placed above the bulb and sometimes below the bulb? Or is it always below the bulb that it's placed?
Well, here it's always below the bulb, but on the early finds, it's sometimes placed on the upper slope of the bulb. So, but you could reach this only with some slider mechanism. Then on the Megara, on the Berlin, it's the higher one is on the bulb, on the lower slope of the bulb, and the lower one is on the cylindrical section below the bulb. So there are all kinds of configuration. But in later evidence, it's always below. So in Mero, it's always, no, in Mero, it's not always below the bulb. It's below the bulb if, yeah, in most, but in the long pipes, we got some in the bulb. Yeah, low, and a very long, slender slope downwards, which is funny. But there are others also in the socket of the bulb. Yeah.
I think
course, we thank both of you because it was a wonderful. We just saw some of the things a couple of weeks ago, and now we see the result of what we found. Okay, so I think we can go on. So Marco, you can come and give your presentation. I think we can go on now with the other two presentations, so we finish not too late. Okay, thanks.
Thank you very much. And as you saw yesterday with Federica Pozzi from Benaria Reale, today we are going to see some scientific results from the analysis that we perform on some sample that was already detached from the tibia. So we could analyze them in our laboratories, and the results that you will see are made by a collaboration between our university with our laboratory, our Vedi laboratory here in Cremona from our department of musicology and cultural heritage, and a center of cultural heritage of our university. And at the same time, the archaeogenetic laboratory. We have a great archaeogenetic laboratory in our university. And the University of Bologna, Department of Engineering and Cultural Heritage, and of course with the collaboration of National Archeological Museum of Naples. So we tried to study those materials, and we at first we had different aims. The first aims with our archaeogenetic laboratory was to try to find, to get some genetic materials from the bone in order to identify the animal of the bone. And at the same time, we characterized with the University of Bologna and our laboratory the tibia, the alloys, of course, of the tibia, and try to evaluate a possible construction procedures. Even we analyzed the alteration process, so the gradation process that we found on that kind of alloys. And at the same time, we tried to characterize if there were some organic material maybe on the surfaces. So we start with the first analysis that was performed. Is a sad story, this, because as you will see, we didn't get any results. It was very complicated, as our colleague from University of Pavia told. But by the way, we have this incredible and great ancient DNA laboratory that work on archaeological materials in our university in Pavia, and they try to get some genetic material from the bones that we got from MANN, from National Archeological Museum. But unfortunately, we got the, as they say, LTB, so lower than blank amount of genetic material. And it was not possible. The area that you see, it was an expected area with some results that we could get from this analysis. We have other samples from museum. We will continue to try to get this kind of information. And me and Eleonora, we were involved in the project, in the national project, research project, with the group of archaeogenetic in Pavia, because they are going to analyze the bones of ancient Roman in order to study the possible disease of the ancient Roman. And we took a little piece of the project, try to continue in the research of the tibia, of the bones, of course, try to see if we can get some information. Till now, it was really difficult, even if they tried to concentrate what they got, but it was not possible till today. But I hope that I can give you good news as soon as possible. So we arrived to the characterization of the materials of the alloys, and we got several samples from the boxes of the museum. And as you can see, the first analysis that we performed, it was to understand the degradation process, the oxidation process of the alloys. So we got different materials, as you can see, cuprite or azurite or malachite, that are typical of the alloys and the degradation process of this kind of materials. And we analyzed all the samples, but I just show you some of them because of the time. And we use different instrumentation to analyze them. And of course, we try to understand the original alloy and all the characteristics of those kind of materials. And what we found is it was a very interesting situation with some case that is going to be analyzed, and with some question. So the first sample, as you can see, we found a copper and a tin in a high percent weight, and but this, as almost all of them, totally mineralized. So we totally lost the metallic alloy. It was completely mineralized. And here you can see all the phases that you can find in this kind. So malachite, cuprite, and so on. And for organic point of view, we found a wax as probably used as protective, and used probably in the 19th or 20th century. And we found a lot of organic material, but the wax was the main organic material used to preserve probably those kind of materials, those kind of tibia. As you can see, this is a mapping that we perform. You see the element of here. You can see copper, for instance, that is present in all the cross section, and of course tin. So this is of course bronze, and you see that we have a phosphorus coming from the bone, and we have in every sample chlorine that comes from the ground, because we are close to the sea, of course. So in almost all the sample, you will see the chlorine element, often associated to sulfurum. So probably a sulfate or something like that present in the material. Here, another example of bronze. Even in this case, the fragment is highly or totally mineralized. And you can see even here the presence of tin, but we have a presence even of lead in this case. So we could think regarding a ternary alloy. But as organic protective, we found here a siccative oil. So an oil was used with the aim to protect the surface. And in this case, it was interesting to see, of course, the alloy and the mineralized phases of the tin and alloy, so the bronze. But you see that we found the lead concentrated in external part of the cross section, and is on some way associated to the presence of sulfur. So maybe this could be solder used for the tibia, and could be an hypothesis. And another cross section was very interesting. In this case, we analyzed the bronze, but you see in the center of the cross section the real bronze, so the metallic of the alloys, original alloy. And this was very interesting because we could see, even in this case, a wax as protective of the material, but you see that we could analyze exactly the composition of copper and tin in the alloy. I can continue because till now, as you saw, we analyze a very defined alloy. So we analyze only bronze, mineralized or not, and now we started to analyze brass. So the other alloy that we found is brass. As you can see here, we have a 12% in weight of zinc. And even in this case, we had these slices are made by metallic brass, and all the other part of the cross section is mineralized. And even on this tibia, on this external part, we found wax as protective. So it seems the wax is the main organic material that we identified. As you can see here, there is the mapping, but it's important to for us that we study this kind of materials to concentrate in this distribution of copper and zinc, because they seems to be separated. You see that here we have a copper, and just a little part of the zinc is present in the associate with the copper, but the most part of the zinc is separated. So probably, I don't know, probably this could be zincification is a process that can divide in the alloy zinc by copper. But it's something that we have to study more, but it's very interesting to see this situation here. Another brass, in this case totally mineralized, with a lower concentration in zinc, with all the oxidation phases that you can see of the degradation process that we can find. And even in this case, the wax was the organic material. And the last was very important cross-section, because in this case, we had a very low mineralized part that you can see in C and B. So in this area, we had a mineralized process of the alloy, but all the cross-section was made by metallic brass, metallic alloy. So that was very important for our colleague from University of Bologna. They work in the metallographic process. So to have this kind of thickness helped them to analyze characteristics of this cross-section. And as you can see, they could have this kind of magnification in this chemical etching with acid chlorine, just to confirm a recrystallization process here in the whole thickness of the sample. And this sign that you can see here are the sign of this process of recrystallization that indicate a final cold working step after a hot working. So it seems that from this information, we can say that in application, the last part of the working so the procedure, the construction procedure, was performed in a cold condition. And this is very important and not so spread information that we can get, especially in this kind of material. And now I just show you a case that was very surprising her, because it's something that we didn't see before. But before, I want just to remember the EMA project, that probably all of you know this kind of project here. And I had a long conversation with Professor Claudia Pelosi. She's a colleague and friend of mine. She's a conservation scientist too, from Università of Tuscia in the center of Italy, not so far away from Rome. And it was my pleasure to have even a conversation with Professor Peter Holmes. And after that, I just want to show you that, of course, one of the part of that project was the analysis that were performed by Claudia Pelosi on two tibiae were examined by a different way, different instrumentation that we use till now that I showed you is non-invasive analysis, X-ray fluorescence spectroscopy. And one of the tibias is preserved in the Archaeological National Museum of Naples. And Claudia found there the presence of bronze alloy with a low tin content. At the same time, she found there trace of silver on the materials. But she could analyze, even together with Peter Holmes, Professor Peter Holmes, even another tibia from Pavia Museum that were studied by Olga Suskowska, a researcher and a musician, and she was, I think, I don't know if, probably she's already got the PhD, but she was a student of the PhD. And Claudia obtained the results that were ascribable to the presence of bronze and brass at the same time. And thanks to the fragmentary state of Pavia tibia, it was possible to examine the different layers and to reveal that the bronze constituted the internal part of the metal stratigraphy, and the brass was in the outer side of the tibia. So it was like we had two different layers, well separated. I can't show you the results because the results has been not published till now, but talking with Claudia Pelosi, I can tell you that the results that I will show you now are really compared with what they got in this analysis. So this is the results that we obtain on another cross-section from National Museum, Archaeological Museum of Naples. And as you can see, we found a brass that are characterized by these two slates of brass, metallic brass. So this is the metallic alloy is still present, are parallel, perfectly parallel. And as you see, we have almost 300 micron of thickness between the two those slices of brass. And for the analysis that we obtain, as Claudia Pelosi analyzed, we see the brass, of course, the presence of zinc, as you can see, around 10%, but even the presence of tin. So we can say by the alteration process of this cross-section, if this was made by, it was present the bronze too, together with brass. Talking with Peter Holmes, he said that the tin could be a contaminant from the ground. So we can consider even this hypothesis in this cross-section. By the way, I just want to show you the mapping that for element that we got. And as you can see, we have copper and we have zinc here. And you can see that we have a quite amount of tin even in the internal side of the cross-section. And what is important to say, and of course as Claudia found, we have some low content of silver too. What is interesting, as you can see here, the two slices in the visible cross-section, in the electron image at the microscope, you can see the two slices are still evident. And in the element of the zinc, you can see that the zinc is present all along the slice here. So it's not present in the middle of the two slides. So if it's brass, was made totally by brass, probably we had a different content and different relation in the content of the element copper and zinc. So we had probably a different degradation process of the cross section. But if you have, in this case, the same case that Claudia, that we found in Pavia Museum, of course we should expect two different material like bronze and brass together in the same section. So this is very important. We will try to use new analysis just to understand well this cross section, to try to understand if there is something to better analyze. But it's important to say that all those are preliminary results. So it's very important to continue in this research, just to have new materials and try to understand if we can have some other case like this. And it's important, those information, even for all that we heard during these days in this Congress, but even for conservation point of view. And the next presentation is on conservation and potential restoration of the materials. So those information that we got, it could be very important even for construction procedures knowledge, but at the same time for a conservation of those materials. So thank you very much for your attention.
Thank you very much, Marco. I think things are really getting interesting and more, I think. Okay, do you have questions? Yes.
Yes, so I want to ask, because from what I understand, I'm a philologist, so I know nothing about the things you're talking about. But if you can see zinc and copper a bit like separate, is it possible that it comes from the alloying process of the two elements?
Yeah, could be.
I was interested in brass from the philological perspective as well, how it was presented in the sources, and I understood it was a very rare material. I'm not sure if it was still that rare in the 1st century AD, but in the Greek period it was quite rare and was used for, or esteemed especially for its appearance. So in this way I would expect it was used for the outside of the instrument because of the color, for instance. So like the inner layers could be made of brass, could be made of bronze, because bronze was more common and it was easier to alloy bronze because it had because tin and copper could have the same melting temperature. Whether zinc has got a higher melting temperature, it was so that the technological process was more difficult. So the metal was simply rarer and more expensive, and they used it just because of it was shiny like gold. So that's why it could have been used for them.
I agree. And as you see in the Pavia, of course, as you know, bronze was the internal part of the stratigraphy, and the brass, of course, was in the outer side. But in our case, so probably this cross-section was made by brass, only by brass. And I think that Peter Holmes was right in considering the thin just
contamination.
Yes, a contamination. What is interesting is why those two slides are still in a metallic state. So probably with a different concentration or different alloy, I don't know. We have to understand. All the section, as you can see, is mineralized.
And are you going to look into the alloying process, how the metal was obtained? Like, especially brass?
Yeah, we will try. We will try.
Thank you.
Yeah, before I start my question, I would like to emphasize that as a side effect, we for the first time have good data about the distance and therefore the thickness of those metal elements, because we only had those corrosion products and tried to assess this roughly. Now we can measure it on your photos, and it's an incredible step forward. Yeah. So my question is, cold working, I guess that doesn't involve filing or lathing, but that involves something that changes the crystalline structure, right? That would be kind of hammering, something of that kind?
Yeah, it could be, yes, of course.
So it,
yeah.
So it would need to be something,
yeah.
Which is fascinating because
fascinated, yes, I agree.
So you might have them thinner or thicker or something like that. Still keep them cylindrical.
Thank you.
Thank you so much. At the University of Reading, we've just started a process of looking at the Reading Aulos there, and we've done some kind of semi-quantitative PXRF, and this is another case where we have brass, copper, and silver. I'm particularly interested in thinking about this in terms of craft specialization and the extent to which particular alloys are being used and the extent to which the alloys may differ compositionally to those found in musical instruments compared to, say, your run-of-the-mill standard kind of brass and copper that are being used. So I'm collaborating with Peter Bray on that, and that should hopefully provide some more things. But are you interested in what are you looking at comparing this with broader databases of metals, thinking about how musical instrument makers may be specializing in alloys in a sense, or?
Oh, I don't know. This is some way. This is a good question. Please consider that we analyze only 6 samples till now, so that's not a statistical enough for our research. So we need to continue, of course. This is a really preliminary results. So even in the composition of the alloy, so the presence of the zinc and the comparing of different elements is too early to say something that could be valid from scientific point of view. But of course, we expect to go back to the museum and to continue in those kind of analysis.
Thank you. I'll have a few more questions later.
Yes. Okay.
Anybody else? Okay, if there is no one else, we can, I think, go on. So other questions can be made even later. And so I call Luciana and Claudio for the last presentation of this session. Thanks.
Oh.
Okay. Hello, everybody. First of all, I want to thank Eleonora and Marco to have organized this interesting conference, and I want also to thank all of you to resist until the last presentation today, and I want also thank all the speakers before me, because as I am a restorer and my main field of interest is not the ancient musical instruments, I learn a lot in these 2 days. So thank you very much. And I'm sure that coming back to Rome, probably I will walk along the Tiber looking for fibers and for things to make my own aulos next days. But anyway, going to the presentation, we saw yesterday the presentation of Eleonora. Yes, thank you. I'm not Claudio. We saw yesterday the presentation of Federica Pozzi about the Venaria Reale school, but I want to remember that we in Cremona, we have a school about the conservation and restoration of musical instruments. This is the only course about this subject in Italy, and it's 5 years course about many kinds of instruments, about the scientific instruments, but also about the string, how bow and plucked string instruments, organs and keyboards instruments, and wind instruments. And at the end of the course, our students have the qualification of restorers according to the Italian laws. Claudio and I, we teach in this course. Okay, going back to the project. The project of about the MANN instruments involve some archaeologists, diagnosticians, musicologists, but also restorers. Restorers, because the restoration is an important moment which allows to understand better the quality and the characteristic of the single instruments and to preserve it to the future. And that is, I think, very important because, as you have just seen, the problems about the archaeological instruments is that from time to time they lose some part and they have today many problems. What are the problems about the archaeological finds? The precarious condition of discovery, for first, the improper handling during the story inside the museums and the deposit storage, and sometimes the unsuitable environmental conditions lead to a deterioration and loss of fragments. This is the picture that we just saw in the presentation of Kamila. We worked on the same instruments because we are in the same group and we work together. And what can we restorers add to the observation made by Kamila? We can see something from the point of view of the restorer. They are stored in this inappropriate case. At the origin, this is a very old photo, but it seems that during their story, inside the storage of the museum, they were stored in inappropriate case. And it's possible to see the presence of many metal oxides. And this is normal because the archaeological finds are covered by oxides because of the burial. Then we don't know anything about the environmental conditions of the storage during the years of the storage from 93 to now, up now. The good things that we can see in this picture is that the metal elements, there are many metal elements, unfortunately now disappeared, but we have the possibility to see them in this picture, in this old picture. And the instruments are almost intact, not fragments, as Kamila said before. They seem to be intact. What is the situation now? This is the situation, as you saw also before. What can we note from the point of view of the restorer? That there is a worsening of the oxidative situation because the oxides are spread around and not only present in the places where it can be seen in the previous picture. Then there is a fragmentation that it was impossible to see in the old photo. And there is the loss of parts. Some parts are disappeared. We have no records of previous interventions, even if, as Marco said before, he found some traces of wax or oil on the surface, but we have no traces of this, no recording of this. The good things, the only good things that I can show here, is that now they are stored in a more suitable case. Made by Etafoam and more adapt to the situation. Yes, thanks to Maria, I know. And then the group of restorers decide to focus their attention on this instrument, the B, the letter B of the group of instruments. And that's because this instrument is representative of all forms of degradation present of the others on the group of instruments. So we examine only that instrument. Okay, which is the first step for a good restoration work is making a photographic documentation. We photograph the whole instrument, a general view of the instrument, both sides, and then we made some details photo and macro photographs of the areas more interesting for us, for document the conservation state. Then we saw, and we had confirmed by Stefan and Kamila, that there are three different materials, three different layers, three different overlapping materials. The bone, the organic materials, a layer of copper alloy, and the second layer of copper alloy on the top. And the two layers of copper alloy are often melted together because probably of the heating during the eruption and other situation during the burial. The second step in restoration work is to make a graphic documentation, and that's because the graphic relief is clearer than the photograph. As you can see in the graphic, it's possible to see the difference and also the division inside the instruments that is impossible to note in the photograph. And so it allows, the graphic relief allows the recording of information and observation made during the work. The tables that we make are three, the main tables, the tables of the materials, the table about conditions, and the table about the planned interventions. The first table about materials records the different kind of constituent materials. We have organic material and copper alloy, only two, and in this case is not opportune to note the different layers, the different overlapping of material. The second table is about conditions, and these tables involve a very, very close observation of the object. For example, in this case, it's possible to note that on the organic material, it's possible to see the very spread stains of metal oxides, of course coming from the metal parts, and that the copper alloy is very deeply oxide. And also we note some cracks, and we register it on the table to identify and to find it better. The second table about condition, we have to divide into the table of about conditions in table A and table B, because it was impossible to overlap the different information in the same table, in the same drawing. So we had two different tables. This is the second about conditions, where we recorded the missing parts, only the missing parts. The missing parts only of the organic material, and missing parts of metal. And we note that in sometimes the both layers of metal are missing, sometimes only the upper layer, sometimes only the lower layer. Sometimes all disappeared, upper, lower, and organic material. And we record this in this table, with different color, of course. The images explain better what we record, what we are recorded. The table 3 is about the planned intervention, what we think it will be good to do on the surface, on the object, to better preserve it for the future. Of course, we didn't do it yet. It's only a planning. This is only a pilot project. It's not completed, realized. And what we plan to do, what we think it will be better to do in this case, to use the sapiolite. This is a kind of clay, very thin clay, mixed with water. It's really very absorbent. And so it's possible to partially, because it's impossible to remove it completely, to partially absorb the metal oxide from the organic material. And so a compress of sapiolite, of clay, on the organic parts can lead to absorption of the metal oxides, or even to light the stains, to eliminate the surface of the green stains on the surface. Then to reduce the oxidation. The oxidation parts are very dangerous because they continue working on the surface, leading to the complete loss of the metal. And so it's better to eliminate the parts more aggressive, the superficial parts more aggressive, with a micro drill, with some very soft brushes, or even stronger brushes in steel, but using it very, very slowly and with great attention. It's also possible, I didn't notice here, it's also possible to use a very light sandblasting on the surface with, of course, very, very soft materials like wood, powder of wood, something very soft, some very soft powder to eliminate the crusts and the oxidation on the surface. Then to connect the cracks and also to connect the detached part, it's possible to use the epoxy resin. The epoxy resin is very stable. In normal condition, doesn't change in color and doesn't lose the properties of joining the detached part. And so this is a part of the project of intervention. The last part of intervention is the protection of the surface. We have to protect it against new degradation. The protection is different depending on the material that we have to protect. For example, on the bone, on the organic material, we can use the wax, microcrystalline wax. Spread on the surface, it protects against the condensation, protects against the powder. It's easy to clean it after the treatment with the microcrystalline wax. And the metal parts it's better to protect the metal parts with a resin, an acrylic resin, like this Incralac. Incralac is a special acrylic resin mixed with benzotriazole. Benzotriazole is a protection against new oxidation of the metal. The two products are mixed together in this ready-to-use product, and it's easy to spread on the surface with a brush, and it's immediately absorbed by the metal and doesn't leave a shining surface, and is very useful to protect against new corrosions. What else? We think that the new protection, the new case is better than before, but it's possible to have a better protection against new damages. And so we think to use the 3D technology. How we did it? Okay, we had a first scanning of the instrument using this machine that we bring to the deposit of the museum, thanks to Maria, and we had a scanning, reply, modeling of the instrument. Then, Ecco, then we have the negative. We modeled the negative of the instrument, the exact tailored modeling of the, here it is. You can see it from different point of view. And this is a model, a virtual model of a case. Then we try to connect virtually the instrument in the case to test if it's possible to realize this case containing the instruments, preserving it from the dust and from not the better environmental conditions, because we don't know if, we hope that it will be preserved well, but with this kind of case, it's impossible to have new damages after protections for many years. Of course, not for forever, but it's a good protection for many years. Now we have the virtual model of the case, and it's possible with this virtual model to realize with stop because the noise is and the milling machines works on polystyrene, that is a very insulating material, and warrant the insulation and the protection of the object. Of course, we have this project, and the results of this, we hope it will be realized, and it's possible to have the same process on all the instruments of the collection. But why we did a conservative pilot project? Because it's possible in this case to study the current conditions and to prevent further decay for the future, because the correct observations allow to add information to the study made from the musicologists, and also it allows to understand or to remedy the damage already present, if possible, if needed, with the same relief, with the same 3D result, we can realize also a support for a musealization if needed. But at the moment, the instruments will go back to the storage. So we only projected a case, a better case to preserve it for the future in the storage. Of course, the project is transmitted to the museum for future development and applications. And that's the end. I want to thank the people who helped us to realize the 3D scanning and the restitution and animation, and you for your attention. Very short presentation.
I think you have seen all the project, so from the start to the could be the result, the future. Yes. Thank you very much. And because usually we are used to ask to have access to material, to study the material, to know, to get information. But here we can also. The idea is also to give back these results to the museum, to everybody who is going to enjoy this material. Yeah.
We hope with an adequate funding we can realize the whole project of protection of the instruments. Maria.
Is there any question, curiosity, or yes?
Are you?
Yeah, this is fantastic.
Do you like our case?
Yeah, we've been working in parallel, of course. The few days we have at the museum, you in your one room, we at the other room.
Yes.
So we haven't been talking enough, so you can also see what we have not been doing in our project. Because while you have scanned the remains of instrument B, we have established how much is missing from this instrument, and that part of it may stay inside the other thing. So in the end, we will need to adjust for additional 58.5 millimeter or so.
But yes, I think we have to share better our information for the future.
No, the problem is that the last time we went, it was 2 weeks ago. So
No,
we couldn't. Yeah, it's really.
it's very difficult to organize also the visits to the museums
all together, because we went. We just met for half a day, and then she had to go back. So we couldn't really exchange the information enough. But this is just to show it was important to have all the steps represented here, just to show what is possible to do. What the possibilities of this kind of project could be for an entire collection. I will start to talk about it as a collection, because
it's so impressive to see all the different elements of this team. I mean, this afternoon really is a highlight to see so many different aspects coming together. And I'd particularly like to commend your attention to the case. That cases are often neglected. It's not just museum objects that get damaged, but as a player, the protection of extremely valuable instruments, that keeping them in good working order is, so...
Yes, it's our task. We are restorers, conservators, and so it's very important to us to, even every time we finish a work on whatever object, we are very worried about the survival of this work, because I'm old enough to have seen many of the objects that I restored when I was very, very young destroyed again, in need again of restorations. And so now I'm very worried about the survival of the objects, and I always think about their protection after the restoration, because the restoration is a very important work, is a very important moment, but after, we have to think about after the restoration, what happens after the restoration. Even if the object is musealized, is stored, not in a storage, but in a room of the museum, even if it's there, it's not, we are not sure that it's well preserved. And so it's very important to think about it, to plan a maintenance, always plan the maintenance, to see the object from time to time, not to abandon it in a storage, but to follow the object and to spend some time to preserve it for the future. Even now, to think about the survival of this object. Now we are talking about them because they survived in a way, but it's important to preserve it for the future, because we are losing them. And so it's very important to think about it, I think.
Well, congratulations to all.
Usually at the end of a restoration, we give a long list of preventive conservation indications. So.
Always disappointed because nobody follows it.
This leads to the question about the resin you are planning to use for putting the various fragments together. Is this reversible?
The glue?
The resin glue.
Yes, the glue is reversible because the epoxy resin is sensible to the heat. So it's possible to heat it only in that place, concentrating.
80 degrees?
80 degrees or more. but is sensible also to low degrees, and it's very easy to remove. It's very easy to remove. It also in difficult situation when the object can't afford the heating, we can use a primer, that is a treatment made before on the surface before applying the glue. It's possible to put some acrylic resin, for example, that is sensible to the solvents, the polar and the polar solvents. And so if you have a layer of acrylic resins under the epoxy resins, you can easily remove it with a solvent. And that it detaches without any heating. The resource knows a lot of things about glue. We studied a lot about glue because it's one of the most important things that we do to stick together parts, detached. So
in Boston, we've been using something that is dissolvable with acetone, which proved very useful because sometimes we had to take things apart again to study the inside.
I heard yesterday that some restorers used a lot of paraloid B72. Paraloid B72 is a very good material, but is not so strong to stick together parts. And so we don't even use it from years. We only use paraloid to protect the surfaces. But in this case, I suggest not to use paraloid because paraloid penetrates too much into the materials and it's impossible to remove it completely. But it's very useful to put a layer of acrylic resin like paraloid B72 before the glue, before the epoxy resin, because it's easily to remove the epoxy resin only with the injection of solvents on the surface, and the glue will detach.
Great. A few of the bits cry for immediate gluing because some are in 3/4 and very small parts that might easily get lost by handling.
You have 2 restorers in your group. Okay.
I thank all of you, the audience, the speakers, and let's hope that this project can go on, and we are going to apply again for the renewal of the agreement, because we have an agreement right now which is going to expire in a couple of months, but we are going to renew it. So finger crossed, and we go on. Thank you very much. Thank you.